In this video, we're going to cover what we call complex fractions. An informal definition of a complex fraction or complex fractions are fractions that have at least one fraction in its denominator or its numerator. They have at least one fraction in the numerator or the denominator. All right, there we go. And so what we're going to do is we're going to learn how we can simplify these complex fractions so that we can have one single proper or improper fraction, what have you, just as we've done when we've added, subtracted, multiplied, and divided fractions before. We want to have one single fraction. We're going to start off with a complex fraction only involving numbers. We have 3 plus 1/8 over 2/3 minus 5/12. There's actually multiple ways that we can simplify these complex fractions. I'm going to stick to one way in this video here. What I'm going to do is I'm going to look at all of my denominators within my complex fraction. For instance, I have an 8, a 13, and a 12. And my goal here is to find the lowest common denominator of each of these denominators here, right? So I want to know the LCD of those denominators. Well, the lowest common denominator, once again, is the least common multiple. Multiples of 8, multiples of 3, and multiples of 12. The lowest common denominator would be 24. Okay? And so I'm going to multiply the numerator and the denominator by 24. All right, remember, I'm multiplying the top and the bottom, so I still have an equivalent fraction here. And I'm actually going to write this stuff out when I multiply so that we won't get a little confused here, right? I'm going to have a 24 times 3 plus 24 times 1/8 all over a 24 times 2/3 plus 24 times, oh, that's going to be a subtraction, minus a 24 times 5/12. Now, some very nice things happen here, right? Well, 24 times 3 is 72. But here with these 8 and 24, 8 goes into 24 3 times. And so we're left with 3. 3 goes into 24 8 times. So we're left with 16. 8 times 2, which is 16. And 12 goes into 24 2 times. So we're left with 2 times 10. 2 times 5, which is 10. And so we'll end up with 72 plus 3, which is 75, over 16 minus 10, which is 6. They both have a common factor of 3. So we'll get 25 over 2. Okay. Notice this is a single fraction, right? They don't have any other common factors, so we're going to leave our answer just like this. So 3 plus 1/8 over 2/3 minus 5/12 is the same thing as 25 over 2. All right. We're going to use the same method here to help us when we have variable expressions. For those of you who like steps, here are some steps we're going to use, right? It's going to be the same as numerical complex fractions, which we just had an example of. We're going to multiply the numerator and the denominator by the LCD, and the rest is just simplifying. Let's look at this first example here. I have 1 minus 13 over x minus 30 over x squared, all over 1 minus 5 over x minus 14 over x squared. And that's a period at the end there. Okay, first thing I'm going to do is I'm going to find the lowest common denominator. My lowest common denominator in this example is going to come from me looking at each of the denominators of every fraction here. I have x and x squared. And what we said before was our lowest common denominator of variable expressions, when they're single variables, are going to be the highest power. We're going to involve the highest power. And the highest power of x here is 2. And so what we're going to do is we're going to multiply our numerator by x squared. And we're going to multiply our denominator by x squared. When we do that, we set ourselves up for a distributive property in both the numerator and the denominator. So I'm going to write it out. I'm going to have x squared times 1 minus x squared times 13 over x minus an x squared times 30 over x squared. That's just my numerator. Let's go to the denominator. We're going to have an x squared times 1 minus x squared times 5 over x minus x squared times 14 over x squared. And now the rest is just simplifying, right? X squared times 1 is x squared. We got to be careful when we get here, right? Remember, if I don't have, when you're multiplying a fraction by something that's whole, you can always put your whole part over 1. And as you can see, one of the x's cancel with the x's in the x squared. So I'm just going to have x to the first power. So that's going to end up being minus 13x. Here, the x squareds cancel. I'll just go ahead and cancel them here. And I get a minus 30. All right, those x squareds canceled. All right, let's look at our denominator. I get x squared times 1, which is x squared. Here, again, we can write that over 1, and one of the x squares cancel, so we're left with minus 5x. And then again, these x squares cancel here, so we have a minus 14. So we've gone from having complex fractions. We multiplied the numerator and the denominator by the LCD, and that cleared all of our fractions. All right. If we didn't multiply by the LCD or some common multiple amongst all of those denominators, then we wouldn't be able to get rid of those fractions. So we're perfect now. We got a numerator and a denominator, one single one, no fractions within fractions. And now all we have left to do is to simplify. So let's factor to see if anything simplifies. X minus 10, x minus 3. X minus 7, x plus 2. And if you notice, I've made a mistake here. They have to multiply to give me a negative 30. So one has to be positive, one has to be negative. It's actually going to be a negative 15 and x plus 2. Okay. Now that I've factored, let's make sure we factor that correctly. And then we can cancel our common factors. And so our final answer would be x minus 15 all over x minus 7. So that is what this big, ugly, complex fraction simplified to. Let's look at more examples. In this example here, we have something very similar. All right, let's look at our denominators. This time we have numbers in our denominator. For instance, we have a 64, we have an x squared, we have an 8, and we have an x. So our LCD, when we look at our LCD, it's going to involve both numbers and variables. Let's look at our numbers first. Remember, lowest common denominator is lowest common multiple. All right, so 64 and 80 and 8, those numbers, the LCD will be 64. And with our variables, we take the highest exponent. So what we're going to do is we're going to multiply our numerator by 64x squared. And we're going to do the same thing for our denominator, 64x squared. And so when we use our distributive property, we're going to have a 64x squared times 1 over 64 minus 64x squared times 1 over x squared all over a 64x squared times 1 over 8 minus 64x squared times 1 over x. Again, if you want to put your 64x squares over 1, that'll be fine. If not, you can go ahead and start canceling. The 64s cancel here, and the x squareds cancel there. And so what you're going to have here is x squared minus 64 in your numerator. In the denominator, with that 8 and 64, the 8s are going to cancel, but with 64, you're going to have 8 still left over. So you're going to have an 8x squared minus, and with the 64x squared, the x's cancel. One of the x's in that x squared stays. So that's going to be a minus 64x. Okay. So once again, by multiplying by the lowest common denominator, we have gotten rid of the fractions that were within the fraction. And now all the rest that we have to do is to simplify further. My numerator is a difference of squares. So I have x plus 8 times x minus 8. And in my denominator, I actually have a GCF, right? So remember, that's always the first step, GCF, all right? So I'm going to factor out an 8x, which is my greatest common factor. And that'll leave me with an x minus 8. And what's so nice about this is that the x minus 8's cancel. And so we're going to be left with x plus 8 all over 8x. And I'd leave my solution like this. Don't try to cancel the 8's. That's a plus sign. Don't try to cancel the x's. That's a plus sign on my numerator. So we leave our answer like this. Believe it or not, these do get a little bit more complicated. And so let's look at an example where it actually gets a little more complicated. All right, this example here is one of those examples. Okay. If I look at my denominators, I have an x minus 1, I have an x plus 2, and an x plus 2. All right, in each of those individual denominators. All right, when I think about my LCD, now this is the kind of LCD with an actual binomial in your, or binomial more specifically, in your denominator, right? Notice x plus 2 is in 2 of them, so it's going to be in our LCD. We only have to write it once. And also x minus 1. All right, so what we're going to have to do is we're going to have to multiply both the numerator and the denominator by x plus 2 times x minus 1. Okay, so I'm going to multiply the top by x plus 2 times x minus 1, and I'm going to multiply my denominator by x plus 2 times x minus 1. Now I'm going to need some space here because this is a lot. All right, I think I might have enough space here. All right, so when I do this, I'm going to have an x plus 2 times x minus 1, right? Distributive property, 3 over x minus 1, minus an x plus 2 times x minus 1 times a 2 over x plus 2. Okay. And when I get to my denominator, x plus 2 times x minus 1 times 1, that one's nice. And I have an x plus 2 times x minus 1 times a 6 over x plus 2. All right. And so when I get to simplifying, actually some very nice things happen. All right. For instance, here, the x minus 1's cancel. All right. Let me go to this term right here. The x plus 2's cancel here. All right. Nothing cancels here because I only have 1's in my denominator here. So I'm going to go to this one. And then x plus 2's cancel in that set right there. And so my new rational expression is going to be 3 times x plus 2 minus a 2 times x minus 1 over an x plus 2 times x minus 1 minus a 6 times x minus 1. And we're going to have to simplify this. Let's use our distributive property. I'm going to have a 3x plus 6. All right, I'm going to distribute this negative with this 2, so I don't have to worry about the negative later. I'm going to have a negative 2x plus 1. All right, I'm going to use my FOIL method, but I'm going to do it a little quickly so I can save some writing space so I won't run out. I'm going to have an x squared minus x. X times negative 1 is negative x, but I have a 2x when I multiply these, so it's going to be a plus x. And then the 2 times the negative 1 is a negative 2. And when I distribute the 6, I'm going to bring the negative with it, so I'll get a negative 6x plus 6. A lot going on here, so don't get messed up. All right, I have a 3x and a minus 2x. And a 6 and a positive 1. And so when I combine those terms, I'm going to be left with x plus 7. In my denominator, I only have one squared term, that's x squared, but I do have an x and a minus 6, and I also have a minus 2 and a plus 6. And so I'm going to combine those terms. That'll give me a minus 5x plus 4. And last but not least, I'll see if I can simplify any. All right, so I want to find two numbers that multiply to give me 4, add up to a negative 5. Well, a negative 1 and a negative 4 will work. And as you can see, they don't cancel. So this will be our final answer. Okay. So this one got a little bit more complicated, especially since we had those binomials in our denominator. Those binomials in our denominator made a huge difference. All right, we're going to look at one more example, and it does look very complicated, but we're going to see that it's actually not as complicated as it may look. Now, this is a complex fraction, right? We have one fraction on top, highlighted there in yellow, and we have one fraction here on the bottom. Okay, so we're dividing that top fraction by the bottom fraction. When we divide fractions, it's the same thing as multiplying by the reciprocal. And so if I want to solve this problem, well, all I have to do is take the top one and multiply it by the reciprocal of our denominator. Now, you could go ahead and factor everything and multiply the top and the bottom by the lowest common denominator of both of those denominators. That method will always work as well. The choice is actually yours. But since this is a single fraction divided by a single fraction, it might be a little bit quicker to do it this method right here. All right. So I have my multiplication. In order for me to cancel my common factors, I have to have it in factored form. So I'm going to factor everything, as you can see here. All right, and everything is in factored form. Now we have to check ourselves to make sure that we did this correctly, because with that many factoring parts, it's very easy to mess up. All right, I think we've got it, and now that we have it, we can cancel our common factors. By the way, that's a 9. But this is x plus 9 here and an x plus 9 here. Other than that, I don't see anything besides the x plus 10s that can cancel. All right. And so now that we have those things canceled, we can multiply across. So we'll have an x plus 8 times an x minus 9 all over an x minus 10 times x plus 4. And that is our solution. Okay, we have one single fraction. Everything is simplified. We're done. All right, and that concludes our study of complex fractions.